Okay, so in section 5, chapter 5, section 3, we're going to look at the Poisson probability distribution. Poisson. Okay, and that says that the probability of X occurring is equal to the mean raised to the X power times E. So this is the real number E on your calculator. So this is a button you have to find on your calculator. It should look like a little E. And it's E raised to the minus mean, or mu, divided by X factorial. So this calculation takes a little bit of careful calculator work to get it right, because you have to know where your E key is, and you have to know where your factorial key is, and you have to be able to raise a number to a power, and then you have to put it all together. So let's see what we would have in this problem. So it says, in analyzing hits by certain bombs in a war, an area was partitioned into 555 regions, each with an area of a quarter of a square kilometer. A total of 545 bombs hit the combined area of 555 regions. Assume that we want to find the probability that a randomly selected region had exactly 3 hits. So had exactly 3 hits, that's X equals 3. So we want X is 3 here. Now mu is the mean number of bombs per region. So the way we would calculate the mean mu is we take the bomb hits divided by the total regions. So they told us there were 554 bomb strikes, 545 bomb strikes over total of 555 regions. So we would just divide those two numbers. And mu, they want us to keep 5 decimal places here. So this would be 0.98191. So it repeats itself. So to 5, 1, 2, 3, 4, 5, we'd call it 98198. 98198. Okay, then E is a button on your calculator, but if you type E to the first power and hit enter on your calculator, you will find that E really is just a number. It's 2.71828. Okay, now this one doesn't ask us to calculate the probability, but you could. So the probability of X equals 3, you would just plug in 3 for any X's, and you'd plug in 0.981981 for your mu, and that's all you need is those two numbers, and then you can crunch it out and get the probability. But they don't ask us to do it, so let's just see what the questions they ask. So they ask, what does mu represent? Well, mu in this case is it's the variable that represents the mean number of occurrences in whatever interval we're looking at. So we can just jump down here to the answer E. So A is wrong because they forgot the word mean right here. The number of occurrences of the event, that's actually X, so that's wrong. Mu represents a static value. Static value means that the number doesn't change. The number doesn't change. And for our problems, that's going to be E, because E will always be, in any of these problems you do, E will always be 2.71828. But mu can change. In fact, it will. And then the area of each region, we actually don't even have a symbol for that, so we don't need that one. Okay, what does X represent? Well, X is the number of occurrences. B. A describes mu, so that's not right. Symbol X is a variable that represents the number of occurrences of the event. Well, it has to be of the event in our interval. So they forgot part. Static value, again, that's going to be for E, so not for this one. Area for each region, we don't need that. Okay, so the last part of this problem is briefly describe what E is. Well, we kept saying E was our static value, so that's our number that will always be 2.71828. Okay, so 21 is kind of introducing these terms. X is, so I should have mentioned this, Poisson is used for rare things. So it's used for rare events. And if you think about it, so we'll use it for things like hurricanes and tornadoes and in this case, bomb. I mean, if we have this is a pretty big region. If you take 555 times a quarter of a square kilometer each, that's a huge area. So if you imagine I've only got 545 bombs, it's actually be pretty rare if one of them hit a specific region. We'll also use it for things like phone calls. So if you think about it throughout the day, you know, you take 24 hours times 60 minutes per hour, and then you say, what's the probability of a phone call hitting any one of those minutes? Well, that's pretty small. I mean, throughout the day, if you get 2 or 3 phone calls over all those minutes, it's a pretty unlikely thing that can happen. So Poisson will handle stuff like that. Okay, so let's look at 22, where we'll actually do some number crunching. It says, last year a person wrote 128 checks. This problem is kind of dated. Nobody writes checks anymore. And especially nowadays, you might write 2 checks a year. I mean, you're not writing 128. Last year, a person wrote 128 checks. Let the random variable X represent the number of checks he wrote in one day, and assume that has a Poisson distribution. What is the mean number of checks written per day? What is the standard deviation? What is the variance? So mu would be the mean checks per day. So it says he wrote 128 divided by 365. So the only part of this that we have to know is that in a year, there's 365 days. Since they want to look at the checks per day. And if you divide these two numbers, you will get 0.3506. To 3 decimals, we'll call it 351. 0.351. The standard deviation is, we'll use the symbol sigma for that. In Poisson, it's the square root of your mean. So this is only for Poisson. So you would take the square root of the answer we just got. I would do this with the unrounded number, so the 3506, not the 351, and you will get 0.5921. Rounded to 3 decimals, we'll call it 592. The variance, which is equal to sigma squared, that's always true. But if you look at this in Poisson, if the standard deviation is square root of mu and variance is sigma squared, if I square both sides of this, I would get square root of mu squared. This square root and this squared cancel, so you just get mu. So Poisson is kind of interesting in that the variance is equal to the mean. So for Poisson, variance equals mean. So whatever answer you got for this first blank will also go here, 0.351. Probably the hardest part is getting this mean, right? Knowing to divide the number of checks by days in a year. Once you have that, then the rest is just sort of a plug and chug. Okay, 23. The random variable x represents the number of phone calls an author receives in a day. And it has a Poisson distribution with a mean of 6.6 calls. So they're saying mu is 6.6. What is the possible values of x? Is a value of x equal 3.4 possible? Is x discrete or continuous? So what can x be? So if it's a phone call, you'd agree with me that you can't receive 0.4 of a phone call, right? I can't have 3.4 phone calls in a day. I either have to have 0 phone calls or 1 or 2 or 3. So phone calls is a natural number. In fact, the only reason I'd throw out A is because there's no 0. I could get 0 phone calls a day. Any real number greater than or equal to 0. Real numbers are decimal numbers. So that would say, yeah, I can get 3.4, but we just argued you can't. So it's not a real number. So it's got to be C. I can only get 0, 1, 2, 3, or more. These triple dots means this pattern continues. So I would get like 4, 5, 6, ... Keeps going. And again, any real number, no. So any real number is going to be wrong. So is a value of 3.4 possible? You would say it is not possible because x is a, if you recall the difference between discrete and continuous, this is discrete. So we recall that discrete numbers are ones that are finite and we can count them. Continuous are infinite and not countable. So continuous are things like decimal numbers, which there's an infinite number of numbers between 0 and 1. Okay. All right, 24 I think is going to have us actually use this equation, so we'll see how it works. Assume Poisson. Okay, so number of hurricanes. So this is again one where it's kind of a natural disaster, which are rare. Certain areas 6.1 per year. So that's the mean number. So that's mu. So they just told us mu is 6.1. Find the probability that in a year there will be 5 hurricanes. So they're asking for x equal to 5. And that's all you need. One nice thing about Poisson is all you need is the mean and the x value. And so you just need 2 numbers. So let's write Poisson again so we have it handy. The probability of x is equal to mu to the x times e to the minus mu all over x factorial. So the probability of 5 is equal to mu, which is 6.1, raised to the x, so raised to the 5th, times e raised to the minus 6.1 all over 5 factorial. And again, this is a little tricky to type in your calculator, so I encourage you to practice it. You would have to type in, I would probably put parentheses around this to break this up. Get a number for this, 6.1 to the 5th. Get a number for this, e to the minus 6.1. Multiply those 2 numbers, and then get a number for 5 factorial, and then divide those 2 numbers. And if you do this, you will get, on top, 18.943, and on bottom 120. And if you do that division, you should get 0.15 1.785. Rounded to 3, we'll call it 1.5. This will bump this up to an 8.158. Okay, part B says the expected number of years with 5 hurricanes. So expected number is E of X. We just saw this back in chapter 4, the end of it. And if you recall, E of X was equal to X times the probability of X. Well, we just found the probability of X. It's right here. So that will replace this. But the X, you have to be a little careful here. They're looking at how many years would we have 5 hurricanes. So you actually use the number of years as your X value here. And in this case, for B, it says 55-year period. So in part B, it says X is 55. So our expected number of years with 5-year hurricanes is 55 times this 0.15785. And if you do that multiplication, you will get 8.68. Rounded to 1 decimal, we'll call it 8.7. So to interpret this, it means in a 55-year period, we would expect, round that up to 9, we would expect 9 years to see 5 hurricanes in those years. Okay, so we would say, part C says, how does this result from part B compared to recent period of 55 years in which 8 years had 5 hurricanes? So we predicted, the prediction was 8.7, the actual was 8, and they're asking, well, how close was our model to the actual? I would say that's pretty good. We're pretty close to what actually happened. So the result from part B is close to the number of hurricanes in the recent period of 55 years, so the Poisson distribution does appear to work well. Okay. Let's take a look at the next one, 25, which will be very similar to this one. So once again, just for reference, I'll write P of X so I have it handy. Mu to the X, e to the minus mu, X factorial. In a recent year, a hospital had 4,441 births. Find the mean number of births per day. So again, here's this per day idea when they're giving us a year. So we're going to have to divide by 365. So we would say mu is going to be equal to this 4441 births per 365 days. And it would be, on average, about 12.167 births per day. Rounded to 1 decimal, we'll call it 12.2. Okay. Now it says find the probability that there are 15 births. So that's X equals 15. So the probability of 15 births is, I would use the unrounded number, 12.167 raised to the 15th. So I'm just plugging into this formula. We know mu, we know X, times e to the minus 12.167, all divided by 15 factorial. And if you do this correctly, and again, I encourage you to practice this, you will get 0.0753. To 3 decimals, we'll call it 0.075. So there's about a 7% chance that on any given day there will be 15 births. So it is not unlikely or unlikely for a day to have exactly 15 births. So in this class, we use 5% as our cutoff for being unlikely. So we've seen that many times. 5% is unlikely. Anything less than that even. 5% or lower is unlikely. But this as a percentage is 7.5%, just moving the decimal 2 to the right. So it's bigger than that. So we will say this is not unlikely. Still pretty low probability, but it's above our cutoff. So we'll say this is not unlikely for a day to have exactly 15 bursts because the probability is greater than 0.05. Greater than 0.05. Okay. 26 is one where it's not necessarily difficult, but you have to do this equation a bunch of times. So they say data from 14 cities were combined for a 20-year period and the total 280 city years. So they just got this number by taking 14 cities times 20 years, and that's going to equal 280 city years. So you're basically just saying, okay, out of 14 cities, and we look at all their years. It's like when people say we have 50 years of experience at our shop because we have 3 people that each have almost 20 years experience. Included a total of 108 homicides. After finding the mean number of homicides per city year, find the probability that a randomly selected city year has the following number of homicides. So the first thing we have to find is mu, the mean. Well, they had 108 homicides out of 280 city years. So just divide those two numbers, and you will get that the mean is 0.386. Oops. Oof. Be careful here. They want us to round these answers to 4 decimals, so you have to take at least 5 in this number to get these right. So it would actually be 38571. That's a good practice to get into. So when they want 3 or 4 decimals for your answer, take one more than that in your calculations. So they want 4, so I'm going to keep 5. Now, these are each, so you just have to repeat this equation 5 times. So they're going to say, okay, what's the probability of 0 homicides, or 1, or 2, or 3, or 4? So this is x is 0, and this is x is 1, etc. So what we would get is the probability of 0 homicides would be this number, our mu, raised to the 0, times e raised to the negative of this number again, and then it's all divided by 0 factorial. And if you do this, you will get 67996. So we have to 4, we'd call it, this is one of those rare cases where this turns into a 0, and this turns into a 0, and this turns into an 8. So it'd be 0.6800. But then And I'm not going to show all of these. I'll just show the next one, and then I'll fill in the answers. But there's a pattern here. So probability of 1 would be 0.38571 to the first. This second part will never change. So in each equation, you're going to have this e raised to the same number. And now it's over 1 factorial. And then when I have p of 2, it would be this number to the second. This number would stay the same, 2 factorial. And then when x is 3, I'd have this number to the third. This number stays the same over 3 factorial. So there's a pattern here. And if you do this correctly, you should get the following answers: 2623, 0506, 0065, and 0.0006. So if you look at the size of these numbers, the probability of 0 homicides in any given year is 68%, which is pretty high. And then the probability of exactly 1 homicide in any given year is 26%. These two right here are almost 100% by themselves. And then 2 homicides is down to 5%, 3 homicides is 0.6%, and 4 is 0.06%. So very small probabilities as your homicide numbers increase. Okay, now for the second part, they want us to find the expected value for homicides. So this goes back to our hurricane problem. So they say in 190 city years, what would you expect for homicides? So we're going to have our expected formula. And for this, I would recommend making a little table. So you're going to take this x, this 190 is now your x. So it would be 190 times the probability of 0, 190 times the probability of 1, 190 times the probability of 2. So you're going to basically you're going to take 190 times each of these answers you just typed. 3 and 190 times the probability of 4. So you're just going to replace these probabilities with these answers you just got. So it'd be 190 times 0.6800, 190 times 0.2623, etc. So ... And if you do this, you will get oh shoot, I'm sorry, I messed this up. So the results consist of 190 city years with 0 homicides, 74 city years with, so you don't use 190 here. This will be easy to fix actually. You don't use 190, you use the original 280. Use this original 280 for your x. So each of these 190s should have been a 280. Okay, then if you do that, 280 times 0.680 would be 190.4. And the next one's going to be 73.4. 14.2, 1.8, and 0.17. So just like the hurricanes, these are the predicted homicides. Then this whole paragraph here tells us the actual homicides. So the actual was there were 190 city years with 0. So for the 0 one, there were 190. There were 74 city years with 1. So this column would get 74 in the actual row. Then it says there were 2 city years with 3. I missed one. There were 14 city years with 2, so 14, then 2, and there were 0 city years with 4. And now they want us to compare again. So we predicted 190.4, 0 homicides. There were actually 190. For one homicide, we predicted 73.4. There were actually 74. 14.2. So if you look at these numbers, they're all pretty close again. You see that? So once again, we get these numbers are very close. So we would say, yes, the Poisson distribution closely matched the actual results. Okay, just one more calculation, and then the rest are vocab. So let's take a look at it. A rare form of malignant tumor occurs in 11 children in a million, so its probability is 0.000011. 4 cases of this tumor occurred in a certain town, which had 18,469 children. Assuming that this tumor occurs as usual, find the mean number of cases in groups of 18,469 children. So this one's turned around a little bit. We're not calculating, we're calculating mean, but we're not dividing numbers because they gave us the probability. So they told us the probability of a malignant tumor is this really small number. So if we have 18,000 children, to find the mean, this goes back to chapter 4, mean, mu, is the same as expected value. And expected value is equal to x times p of x, which we've seen several times today. Well, we know p of x, it's this really small number, and x in this case is the number of children. So x is 18,469. So we would say, take that 18,469, multiply it by this really small probability, and you would get, out of 18,000 kids, we would expect that 0.2031 of them would have this tumor. So rounded to 3.203. Now in part B, it says, what's the probability that the number of cases is exactly 0 or 1? So this is where we want to use our Poisson equation, use this p of x equation again, but we have to do it twice, one where x is 0 and one where x is 1. So the probability of 0 cases would be, this is our mu now, so it would be 0.2031 raised to the x, in this case x is 0, times e to the negative 0.2031, all over 0 factorial. And 0 factorial is 1. We defined that a while back. If you do this, you would get 0.8161. The probability of 1 tumor would be this 0.2031 to the first power, e to the minus 0.2031, so that doesn't change, all over 1 factorial, and if you do this, you will get 0.1657. The answer to B is just add these two numbers together, and you'll get 0.982 after you round. So there's basically a 98% chance that you're going to get either 0 tumors or 1. The probability of more than one case, so more than one, would be the probability of 2 tumors plus 3 plus 4 plus 5, all of the other ones. And if you recall, the way we handled this before was the probability of at least 1 is equal to the probability of 1 minus none, or in this case, more than 1 would be, so to calculate this, you would take 1 minus the probability of x being greater than equal to 1, but that's the probability we just found. So you just have to take 1 minus the previous answer. And if you do that, you'll get about almost 2% chance, 1.8% chance. So let a probability of 0.05, 5%, our cutoff for rare, be very small, and let a probability of 0.95 or more be very large. Does the cluster of 4 cases appear to be attributable to random chance? Why or why not? So we're basically saying there's only a 2% chance that you're going to get more than 1 tumor in a community. This community had 4. So can we say that this is just chance that 4 kids had this tumor when we expect there to be only a 2% chance of even 1 kid getting it? I would be nervous about living in this area, right? If I expect there only to be a 2% chance that even 1 kid gets a tumor, and I've got 4 kids in this community getting a tumor, I'm testing the water, I'm looking at the power plant, right? Something's going on here. So is this chance? No. Because the probability of more than 1 case is very small. And this is the power of statistics, is you can do stuff like this and you can actually figure out, hey, something's going on here. We better start checking things out. Okay, 28. Fill in the blank. The blank distribution is a discrete probability distribution that applies to the number of occurrences of some event over a specific interval. Well, what have we been talking about all day? Poisson. That's been the theme of the whole day. Binomial, we studied in section 5.2. Multinomial, we'll never even look at that. Hypergeometric, we won't ever look at that. (29) Which of the following is not a requirement of the Poisson distribution? The occurrences must be random. That is a requirement, true. The occurrences must be dependent. We pretty much never want things to be dependent. So that's what we don't want. The random variable x is the number of occurrences in an event. Yep, that's true. The occurrences must be uniformly distributed over the interval being used. Yeah, we assume that things will happen uniformly over our entire interval. Last question. The standard deviation for Poisson was what? It was, so sigma, if you recall, I wrote down was the square root of mu. So it's the square root of mu. This one comes from section 5.2 for binomial. This one we never use, and this one was sigma from 5.2. That will complete section 5.3 and chapter